Hello, this is Rick Mazumder from MathX, and today we're going to be doing the number 12 from the AIME II of 2019. Now, this problem was requested by one of the viewers a couple of weeks ago, so even though it's been quite a bit of time, this problem is quite nice, which is why we're covering it now. So without further ado, let's get into it. For n is greater than equal to 1, call a finite sequence a1, a2, through an of positive integers progressive if ai is less than ai plus 1 and ai divides ai plus 1 for all I greater than equal to 1 and less than equal to n plus 1. Find the number of progressive sequences such that the sum of the terms in the sequence is equal to 360. So this problem isn't very long. It gives us a condition, and then it kind of just wants us to find all the sequences that match the condition of the problem, progressive, and have the sum of their terms equal to 360. So before we even consider the 360 part, let's try to get an idea what a progressive sequence is. So it says that a progressive sequence is basically where each term is less than the previous term, and each term divides each of its following terms. So if we have 1, 2, and 4, this is an example of a progressive sequence because 1 is less than 2, 1 divides 2, 2 is less than 4, and 2 divides 4. Similarly, 1, 2, and 6 is also a progressive sequence. Because once again, 1 is less than 2, and 1 divides 2, and 2 is less than 6, and 2 divides 6. So pretty much this kind of gives us an idea of what a progressive sequence looks like. So let's try to write it out generally using variables. And then hopefully we can set up an expression that we can use to calculate the number of progressive sequences. So let's just say that the first term is x1. It says that it could be a1, but let's just say a1 and x1 are equal. So we have a first term of x1. The next term has to be x1 multiplied by some other value. Let's just call that other value x2. Similarly, the third term can be generated by taking this previous term and multiplying it by another constant, giving us x1, x2, and then let's call this new constant x3. And this can be repeatedly done until we get to some xn term, in which the term will look like x1, x2, x3, xn. So pretty much this is just the generalized form of a progressive sequence. And we can see that if we take the values in our example progressive sequences, we can actually correspond them to the first three terms of this sequence. If x1 is 1, then our first values match up. If x2 is 2, our second terms match up. And then in order for the third element of our first sequence to match up with the third element of our general sequence, we need x3 to be equal to 2. Now if we want our third element of our second sequence to match up with the third element in our generalized sequence, we need x3 to be equal to 3. Nonetheless, this is pretty much the generalized form. And since it says that each term must be greater than its preceding terms, we know that the constants x2, x3, all the way to xn, so xi, where I is greater than equal to 2 to n, each of these xi's cannot be equal to 1. So xi equals to 1? Nope. So we have the general form for a progressive sequence. Now it's kind of asking us to find the number of progressive sequences such that the sum of the terms in this sequence adds up to 360. So after finding this general form, let's try to add up these terms to try to create a Diophantine equation in which we can just count the number of sequence solutions. Because honestly, it doesn't seem like there's much other options. So we can generate this Diophantine equation by just adding up all these terms individually and then maybe manipulating it to see what we get. So doing that, we can write our first line as x1 plus x2 plus x1, x2 plus x1, x2, x3 all the way to x1, x2, x3, xn, we can write this sum as being equal to 360. So now we have this strange Diophantine equation, which we need to solve for values x1, x2, x3, such that they satisfy this equation. They satisfy this inequality up here. So now this equation is hard to deal with as it is. So we should probably try to simplify it into something maybe a bit different. So we can begin by factoring out an x1 from all the terms. So we factor out this x1 and write x1 times 1 plus x2. And then we see at this point, we don't only need to factor out x1s, we can also factor out x2s, because at this point we factor out all the terms which only had x1s. So we can create another parentheses and do x2 plus x3 1 plus x3. And similarly with the x2s, all the terms that had only x1s and x2s are now all factored out. So we can begin factoring out x3s from all the remaining terms. And we see that this pattern continues all the way to xn. So now we have this weird function that will give us the number of progressive sequences for which the sum of the terms is equal to 360. But this function will be hard to attack by itself. So when we have a weird function that looks something like this, we should probably define it so we can call upon it later. So let's call this function f of 360. Okay, so we have this weird function, but we don't really know what to do with it. However, since this function happens repeatedly, we could try to relate it back to a smaller version of itself. So let's see how we'd get from x1 to x2 on the outside. We could get that by simply dividing 360 by x1 and then subtracting 1 from it. And then that would give us the same function but with x2 at the beginning. So now with this equation, we know how to relate the number of progressive sequences that add up to 360 to the number of progressive sequences that add up to 360 based on the first value of x1. So if we take all possible values of x1 and then calculate the f's that result from that, the sum of those f's should just give us f of 360. So all possible values of x1 are divisors of 360. So just by substituting divisors of 360 into this equation, we should get values that we can use and add together to find the value of f of 360. So I'm going to show you a couple of examples and then hopefully you get the idea of what I mean from there. So let's say we're going to just test out the smallest divisor of 360, 1. Let's say x1 is 1. That means that we have that 359 is equal to x2 times x times 1 plus x3, all that stuff. A weird function, pretty much. And it's pretty much the same thing as what we had before. So we dealt with this one by calling it f of 360. So we're going to deal with this weird function with regards to 359 is calling it f of 359. Similarly, if we plug in 2, we got 360 by 2, 180, and then we subtract 1 from that, giving us 179. So we call that f of 179. Oh yeah, so this notation might be kind of confusing. We're not saying that 359 is equal to f of 359. We're going to just say that since the left side is 359, and this is the same function as above, we denoted the number of ways that we could generate a sequence as f of 360. So similarly, since the conditions are exactly the same, it's just that the values differ up, we're going to denote the number of ways we can generate a sequence from this as f of 359. Similarly, we're going to use this 179 and we're going to just calculate the number of ways to generate a sequence from this value 179 as f of 179. So using this, we can generate that f of 360 is equal to the f of smaller terms, like 359, 179, and then any other terms you generate just by plugging in divisors of 360 into this expression. So I think the final one we're gonna get is the final one in which this is greater than 0 is when x1 is equal to 180. And there we're going to get f of 1. Because 360 by 180 is 2, which when we subtract 1, we're going to get f of 1. But there's actually one more case we have to take account. So these cases talk about how to generate different sequences, the number of ways you can generate sequences based on their first terms, x1s. But if we have 360 itself as the first term, it's not going to be taken account for in any of these until the final one, which I guess we could say is f of 0. But since that the value of f of 0 is just clearly 1, we can just write plus 1. So hopefully you should be following along. And I'm going to write what this true expanded form is just so you can check over it as well. So here I've expanded out f of 360 into the sum of all of its like factor f's and 1. And I've also included the general function f of a to remind you how we got here. Basically, we defined f of 360 as the number of ways to get a progressive sequence such that the terms added up to 360. And just by looking at the expression we generated from our just general expression, we realized that the values that follow after are just values generated from this part of the equation, where x1 is any factor of 360. So here I've just generalized it. If we wanted to compute for 360, we would just plug in 360 for a and then divide it by all values of x, where x divides 360, and we're going to get the expression as listed above. So from here, you can check over to make sure the values you generated match up with these values. And then as for how to calculate for each of these expressions themselves, so remember what f was. Like f of a basically means the number of progressive sequences that add to a. So what does that mean? That means if we have f of 5, we just need to figure out the number of progressive sequences that add to 5. Now, that doesn't sound much better, but it's pretty easy to see that the number of progressive sequences that add to 5 is just 1. And that's because the only sequence is 5 itself. So this pattern holds up for all primes. So just like that, you could probably get half of the numbers on this list. You can just replace them with 1. F of 1 included. For the rest of the smaller and intermediate terms, which are not directly prime, you can honestly do the casework to figure it out. So I'm going to just do f of 14 as an example. So f of 14 is just the number of progressive sequences that add to 14. So we could honestly just set up cases. First case is if the first value is 1, we have 1 and 13. Second case is if our starting A1 value is 2, then the second value has to be 12. So this is about it for our 2-value sequences. So when it comes to 3-value sequences, there is no 3-value sequence when it comes to 1, because we can't break up 13 any further. But when it comes to the 2 and 12 sequence, we could do 2, and then we could break up 12 into two numbers that will add up to 12, but one that's going to be divisible by 4, and the other one's that's going to be divisible by the other one. And that's going to give us the sequence 2, 4, 8. So just like that, we can pretty easily, just using casework, compute for these small cases. So f of 14 is just 3. So you can just continue this with the rest of the values. I'm not going to show it step by step because I think I solved the bulk of the problem, and at this point it's just computation. And hopefully on AIME you would have enough time to compute for this. Anyways, the test is 3 hours, so you have quite a bit of time if you need to compute for it. But the computation isn't too bad. Anyways, most of the numbers are already eliminated. As I've said, the primes are all just canceled out and replaced with 1. And you just have to do this casework operation on a couple of composite numbers. The worst example probably being 119. However, since 119 doesn't have too many factors, that itself won't even be that bad. So hopefully adding up all these cases, you get the answer of 47. Because that's how you solve the problem. So this was an AIME 12. So quite a difficult problem. And if you solve this on the test, good for you. And it was not easy by any means. But at the same time, it was not completely unapproachable. We started this problem out relatively simply. We just got a feel for the problem and just set up a general form. The hardest part of this problem would probably be just defining a function and recognizing that this function comes recursively off of smaller iterations. But then once you do that, you just need to use some simple casework and you're done. So I hope you enjoyed this video and hopefully you learned something new about how to tackle hard AIME problems, just hard function and sequence problems overall.